We do research and product development in the area of hot water distribution. So I guess you could say I'm in hot water. Um, and we specialize in improving the hot water performance of residential and commercial buildings. And today's presentation is going to be talking about a particular area that we specialize in, which is on-demand recirculation for homes. I'm going to be talking primarily about residential plumbing, but I'll also touch upon commercial plumbing and then how they apply to the newest building energy codes in Texas. So,
Oh shoot! Hold on a second. Let me see if I can get this full screen here. Full screen.
Jason, can you hear me?
Yeah, I can. Can you hear me? Can you hear me?
I can't hear you.
Oh gosh. I can hear you.
So let's start off with this first slide here. Great. Okay, you can hear me. Perfect. So this first slide, let's talk about how big hot water. Why should we be concerned about hot water? When we're talking about energy performance of buildings, the goal that we're all trying to get to is zero net energy. We don't want to be using any more energy than what we can produce through renewable energy sources. And what this graph is showing is that over a period of time, that hot water is becoming an increasing part of the overall energy pie for a house. So hot water represents roughly 1 to 2, either the first or second largest energy expense for residential homes nationally. You can also see that space heating, is actually becoming a smaller portion of the pie, and that's due to advancement in controls, advancement in building codes with regards to the building envelope. It's getting tighter. So space heating is becoming more efficient, whereas water heating is becoming not necessarily less efficient. It's just becoming a greater portion of the overall energy pie. So it represents roughly 20% of total hot water energy use. Next slide. So why are we waiting for hot water? And this is the million-dollar question, right? I think everybody can relate to this question at some point. You've turned on a faucet, you've turned on a shower, and you've sat and you waited a long time for the hot water to come out. And generally speaking, we all know why we're waiting for hot water, because it has to do with the plumbing, right? Your hot water pipes over a certain period of time will cool down to ambient temperature after the last time you used hot water. And that cool down rate can depend upon a number of factors. Are your pipes insulated? How long are your pipes? Where are they being routed? So that cool down period, it can be anywhere from 5 minutes to 30 minutes from the last time you used hot water. Your hot water pipes cool down, and so when you turn on your shower or faucet, you essentially have to drain out that volume of water to get the heated water coming from your water heater. Now, it might feel like the problem's getting worse, and you would be right. It is getting worse in our homes, and here's why. Because from the 70s to today, the median U.S. home average square foot, or the median square foot, I should say, has gone from 1,600 square feet to 2,500 square feet. So our homes are getting bigger. And therefore, the average distance of pipe from the water heater to the furthest fixture has more than doubled. Your water heater's probably in your garage, and where's your master bathroom? It's clear on the other side of the house. Also, the number of fixtures have doubled over that period of time. And when you've doubled the number of fixtures, it means you have to increase the size of your piping. So our pipe diameter has gone from 3/8 and 1/2 inch all the way up to 3/4 inch and 1 inch typically in residential homes. So you have a much higher volume of water in your pipes that you have to then bleed out. If that wasn't bad enough, your fixture flow rate is being reduced. It seems like every several years it's going down even farther. It used to be, at one point in time, your shower heads were like almost 5 gallons per minute flow, and then it went down to 2.5 gallons per minute. And now the plumbing code is saying 2 gallons per minute. And in California here, we're going down to 1.5. So fixture flow rates are being restricted in an effort to conserve water. But the consequence to that is that it's taking literally almost 20 times as long to get hot water in today's homes than 40 years ago. The result is, according to the Department of Energy, you can waste anywhere from 3,000 to 10,000 gallons of water just waiting for hot water to arrive. And it also results in, dissatisfied homeowners and users, right? What do we want? We want hot water quickly. So let me touch upon some common plumbing architectures, because this is primarily the reason why plumbing is inefficient. So the most common types of plumbing architectures that we see are a trunk and branch, home run manifold, compact design, and then recirculation loop. And I like to use the analogy of a tree because when we talk about plumbing in our homes, we refer to the plumbing in terms of trunk lines, branch lines, and twigs, where the trunk line represents the major artery of hot water. And then off of that trunk line, you tee off the branches, and the branches go to the individual fixtures in the units. And then the twigs are what connect the branch lines to the actual fixture. So here we see a trunk and branch, and these are very basic diagrams that I'm showing you. Obviously, actual floor plans are going to be more complicated than this, but to be simplistic, I just wanted to show you, give you an idea of what they look like. So trunk and branch, you have a single trunk line that extends from the water heater down to the furthest end of the house, and it deadheads at the end of the house, and then you have branches that extend off of that. This, I would say, is the most common type of plumbing architecture, probably the most inefficient as well. But it's done because it's the least costly option for a builder, is to do the trunk and branch, least amount of plumbing. You got your home run manifold, and this is where you have the manifold and you have home run piping that goes to each individual fixture in the house. There's some advantages and disadvantages with home run manifold. There's a lot of water being wasted in these systems. I don't know how common you guys see this in Texas. It's not very common in California, I can tell you that, but it has become somewhat of a standard practice.
We're
Another
seeing it
type
more.
of
Can you hear
plumbing
me?
is what we refer to as a compact design. On the next slide, and a compact design is just that. It is where you have the water heater that's more centrally located in the house, and you keep the trunk lines to the fixtures to a close enough proximity where you're never really wasting any water, or you're never really waiting for any hot water. Now, when I look at this design, I think of the house that I grew up in Minnesota. This was exactly what we had. We had a basement foundation. I was one of 9 kids, and we lived in about a 1,200 square foot house. We had a bathroom and a sink, a bathroom and a kitchen sink, and then a bathroom down in the basement. But the water heater was right in the middle of the house, and so we probably waited 5 seconds at any fixture to get hot water. And then finally is the recirculation loop. And a recirculation loop is where you have hot water extending out of the tank, going down to the far end of the house. And then after that last fixture, you have what's called a dedicated return line that brings the unused hot water back to the water heater. And at the end of that return line, you have a small pump that pumps the hot water through the house. And in this way, you are never having to wait for hot water, because the hot water is being delivered essentially to the fixtures. Now, of all the plumbing architectures that I went over, a recirculation loop, if it's properly designed and operated, will provide the most water and energy efficiency of any type of plumbing architecture. But the key is in how to operate the recirculation pump. It is possible to design a recirculation loop where you never waste more than 1 or 2 cups of water at any fixture of the house, as long as you keep the branch lines within about 10 to 12 feet from the main trunk line and have it be 1/2 inch, you're never going to waste about 2 cups of water. Um, okay, so let's talk about recirculation loops and recirculation systems. Now, this is a type of system that I would say is most prevalent now in new construction here in California. I'm sure there's a lot of recirculating systems in Texas as well, given the size of homes and all the problems that I laid out. But not all recirculation systems are created equally. Um, so let's talk about types of recirculation systems. How do we operate the pump? Well, there's continuous pumping, which is what that just means is that it's running nonstop 24/7. Clearly, that is the most energy wasteful method of operating a pump. There's a thermosiphon or gravity, which is it doesn't utilize a pump and it uses gravity and thermosiphoning effects to move the water through your loop. Very inefficient as well, and is actually prohibited by many building energy codes. They prohibit thermosiphoning. You have time clocks, which put it on a schedule. Um, and the problem with timers is that they can often be imprecise. Think about how often you really use hot water. It can be unpredictable and spontaneous, right? With a timer or a time clock, essentially what you're trying to do is predict when you use hot water. I think most of us, we know when we're going to take our morning shower roughly, right? But then after that, can you really predict when you're going to use hot water? And think about this also is how many hot water events are there actually in your house? I think you'd be surprised to learn, like, in a typical house, there's probably less than 15 actual hot water draws in a given day. Assuming, like, 2.5 people. There's just not as many hot water events throughout the day as you might think. Temperature control. So a temperature control, otherwise known as an aquastat, basically turns the pump off when hot water has circulated through, and it just turns the pump on and off to maintain a constant hot water return line temperature. It's still pumping hot water more frequently than it needs to because you're maintaining hot water through your loop even when you're not using hot water. And then there's a combination of a time clock and an aquastat, which is probably the most common type of system that we see out there. Variable speed drive. Um, yeah, just a couple more. Variable speed drive is a type of pump system that modulates the speed of the pump based off of hot water demand. So it uses like a pressure switch that when it senses that there's a lot of hot water being used, then it speeds up the pump. And when it senses that there's no hot water being used, that pressure switch tells the pump to ramp down. It still results in 24-hour circulation. So while it does save on electricity for the pump, it does not offset the heat losses or the loop losses from constant circulation. And then there's another type of recirculating pump called like a learning or a smart pump. And these supposedly predict when you're going to use hot water. They look at your patterns and they develop some type of algorithm. I think the verdict is still out on these, because number one, hot water, like I mentioned, is unpredictable and spontaneous. And so it is hard to develop an actual pattern. Also, hot water use on a weekday is different than hot water use on a Saturday and versus a Sunday, which is what the data shows. So, until we get a better sense for how these algorithms actually work and predict water or predict hot water draws, verdict's still out. And then finally, there's demand control. Demand control, which actually only turns the pump on when you're going to use hot water. So those are basically the type of circulating systems that exist. The cost to operate a recirculating system. So I always use the analogy of an iceberg, right? You have the top of the line, the cost, which is the cost of the pump, but then you have the bottom of the line costs. And those are the hidden costs of operating a recirculation system. When most people think about the costs associated with operating a recirculation pump, they only think about the electricity for the pump. So if it's a small fractional horsepower pump, maybe it's 100 watts, you know, the thinking is that the energy costs are negligible. Um, whereas the vast majority of energy use and the cost associated with operating a pump is the heat losses through the distribution. So the more often you're pumping hot water into your line, the more often your water heater has to turn back on to make up for those losses, for all those heat losses in your pipes. Um, so 90% of the operation cost is in the loop losses. But then you also have maintenance and repairs. So uh, when you circulate excessively, it promotes damage to damage to your heat exchanger for your tankless water heater. You can wear out your pump faster. You can get pinhole leaks in copper pipes. So that's actually very common for recirculating pumps to cause is pinhole leaks around 90-degree elbows. That's most often where you're going to find pinhole leaks. So there's a lot of costs associated with operating a recirculation pump. So when do you not need to operate the recirculation pump? So there's two times when you don't need to run the pump. When you don't need hot water, right? This is sort of obvious. So if you're at work or if you're on vacation or if you're sleeping or just kind of hanging around the house, you do not need to run that pump. And secondly, if you already have hot water in the line, so if you're already using hot water, you don't need to run the pump because once hot water is coming out of your faucet, that draw flow is moving the water through your plumbing. You no longer need the assistance of that pump. It's only during that transitional period where right before you want hot water and there isn't already hot water in the line, that's the only time that the pump needs to run. So, you turn the pump on, it runs for maybe 30 to 60 seconds before it shuts off, and then that's it. So operating in this fashion is the most efficient way to operate a pump. Next slide. It's called demand controlled recirculation. It uses sensors to turn the pump on and then turn the pump off. So we use a signal to indicate hot water demand, and that can be in the way of a push button activator. It can be a motion sensor. It can be a flow switch. It can be a pressure switch, something that's detecting hot water demand within the dwelling unit. That turns the pump on. When hot water has reached the farthest end of the house, either at the end of the recirc loop or at the end of the line, a temperature sensor tells the pump to turn off. It'll work with any tank or tankless water heater or any heat pump water heater. And in fact, it's the preferred circulation method for both tankless and actually all three. Tankless water heaters have a heat exchanger that tend to go bad if you're constantly circulating through it. And then also heat pump water heaters, which are basically on the horizon as the next big thing in hot water. They don't like to have constant recirculation going through it. It affects the efficiency of a heat pump. Heat pump water heaters generally work best when colder water is coming through it. So keeping the recirc pump off as much as possible only increases the efficiency of a heat pump water heater. Okay, next slide. So the most common way to operate an on-demand system is using push-button activators, and these can be put anywhere in the house. Typically, a builder will put one in each bathroom and one by the kitchen sink. So you walk in your bathroom, you click the button, it pumps, it simultaneously starts your pump, and your pump kicks on your tankless water heater, and it starts to circulate the hot water through. And if you push the button and there's already hot water in the line, the pump stays off. And these can be either wired or wireless. Next slide. And then there's also motion sensor activation. So if the homeowner does not want to push a button, then motion sensing is an acceptable uh, uh, way of sensing hot water demand. You walk in your bathroom, and the next thing it does is it checks the temperature. So again, like let's say you're having a party at your house, right? People keep walking in and out of your bathroom. That doesn't mean that the pump is going to keep turning on, because as long as there's hot water in the line, then the pump remains off no matter what. And you can use any combination of push button activation and motion sensor activation. So, maybe you want to have a push button in your kitchen because you're, most often walking through the kitchen quite a bit and you don't necessarily need hot water. So you can keep a push button in your kitchen, but in like a guest bathroom or a kid's bathroom, you have the motion sensor. There's also some wireless activation options that are out there. Wireless is, you can basically put the activators anywhere in the house. This is especially practical for an existing building retrofit, where it's no longer practical to run the low voltage hardwiring throughout the house. And so, if you have an existing house that has the long hot water wait time, and you want to install an on-demand system after the fact, you can always go with the wireless, and it works just as well. And there's some other types of activation that are now available, such as an LED lighted indicator. So this is it's a little switch that when the light is on, it indicates that there's hot water in the line, and so you know that you don't have to do anything. And then when the pipes cool down, the light turns off, and so you know that you have to hit the switch. So let's take a look on how a demand control looks in a trunk and branch line plumbing situation, right? The typical standard plumbing. You have your water heater at one side of the house, and at the farthest end of the line, you're going to cross connect the hot into the cold water line. So your hot and cold water line are connected at the very end, and that's where the pump is. And whenever you activate the pump, it is going to first of all going to look at the temperature. Does it need to turn on? If there's hot water there, it stays off. But if it's first thing in the morning, or if it's a half hour since the last time someone's used hot water, you activate the switch, the pump turns on, and now it's pulling all of that ambient temperature water that normally goes down the drain, and it's going to pump it through your cold water line and send it right back to your water heater. Now, the way that this system works is that when it's looking for a rise in temperature. So when it sees between a 6 to 10 degree rise in temperature, so in other words, if your hot water line was 60 degrees, that pump is going to shut off when it reaches like 66 or 70 degrees, because all it's doing is it's looking for that temperature rise. That temperature rise indicates that the hot water is just moments behind it. So it's actually turning off the pump before you're sending hot water into your cold water line. So by the time the pump shuts off, you have hot water on the hot water side, cold water on the cold water side. So here's some pictures of what it looks like in an under sink kit application. And in the next slide, you'll see a better shot of where these flex lines tee into the hot and cold water stub outs underneath the sink. So installing one underneath the sink is pretty easy. The most challenging part of the installation, I would say, is that you do need to have power underneath that sink in order to plug in the pump and the controller. If your kitchen happens to be the furthest fixture, almost every kitchen sink has an electrical outlet underneath because of the garbage disposal. But if it's the master bathroom, then you would have to drop that a GFI outlet from above the sink down below. So that's the hardest part of the install. A lot of builders, what they'll do is if they don't put in a recirculating system, they will put an outlet underneath the master bathroom sink so that the homeowner has the option of installing an on-demand system after the fact. Okay, how about a demand control in a recirculation loop? And again, I would say that from the builders that we work with in California, Recirculating loops are the new norm. And so, at the far end of the house, after the last fixture, you have the dedicated return line that's bringing the unused hot water back to the water heater, back into the garage. You have the pump right next to the water heater. You have a temperature sensor that's placed somewhere just upstream of the recirc pump. And then you have the activation, either low voltage, you have hardwired low voltage that's running in parallel from each fixture of the house back to the pump, wherever it's located. Next slide, please. So here's what it would look like on a dedicated return line. The pump right back by the water heater. It's drawing up in this picture. In the next picture, you'll see the return line here. And this is inside of a garage, and you can see where the return line is connecting to the cold water inlet, feeding these two tankless water heaters, and then there's the hot water supply that's going out. So in this picture, you can see the start of the loop, the hot water supply, and the end of the loop, the hot water return. So in a proper recirculation loop, I think it's important that it's not as easy as just as putting in a return line and sticking in a pump. There's also critical components that you have to have on the return line assembly to make sure that you have a properly operating recirculating system. So things like check valves, bleeder valves, isolation valves to service the pump. These are all very essential, and they have to be put in the right order in order for the system to work. And I'll talk about that more in a later slide. The benefits to demand control recirculation versus the alternatives. So with a demand control recirculation pump, the pump runtime will typically not exceed more than about 15 minutes per day total. So let's say if you have 10 to 15 hot water events per day, and you only need that pump to run for maybe a minute at a time, that results in about 15 minutes per day total. The results is that you're going to save just as much water as you did before. So somewhere between the order of 3,000 to 10,000 gallons per year per system, with very minimal distribution losses. The amount of electricity to run the pump is less than $3 a year, and it does not do any premature degradation on your plumbing. So it's not going to result in excessive turbulences that will cause pinhole leaks. And it's the only system that will preserve the full warranty of any tankless water heater. There's a lot of tankless water heaters on the market where if you attach a recirculating pump and you have it run continuously, it will completely void the full warranty of that tankless. If you put a timer on it, it will take that tankless warranty from 10 to 12 years down to 3 years. So if you are using tankless water heaters, on demand is the way to go in terms of preserving that equipment and preserving the warranty. And again, what I was saying before about heat pump water heaters is that heat pump water, on-demand recirc will ensure that a heat pump water heater is running at its most efficient operation. I don't know if you guys have seen heat pumps really hitting the market there in Texas yet, but it's really starting to make waves here in California. They're talking about doing away with all gas water heating. At some point, they want to completely do away with gas water heating and move to heat pump water heating for the efficiency and also to decarbonize water heating to move away from fossil fuels. So
we're seeing very little
anyway,
down here.
So that that portion was regarding residential plumbing. I'm going to touch upon commercial. I'm not going to get too deep into commercial, but I do want to make a distinction here is that when we talk about commercial applications, we're not necessarily talking about commercial buildings. We're really talking about commercial plumbing, right? So for domestic hot water, where you're going to find commercial plumbing are buildings that have a lot of domestic hot water use. So think about apartment buildings, hotels and motels, student dorms, you know, as opposed to say like a box retail, or maybe an office space that has a laboratory and a small water heater that serves a few fixtures. Even though those are technically commercial buildings, we wouldn't consider that commercial plumbing. So I just want to make that distinction. So it's even more important in commercial buildings from an energy standpoint to control the recirculation pump, because of the losses are exponentially greater. So if you look at a typical apartment building that has a central water heater or a central boiler, the amount of energy loss is actually pretty tremendous. Uh, the California Energy Commission estimates that only about 1/3 of all the energy that you put into a central hot water system comes out as hot water at the tap. The rest of it is lost either through combustion losses back in the boiler room, or you got, about 1/3 of it is lost in the recirculation. And that's, the heat losses in a distribution are mainly a function of the surface area of the plumbing. So the bigger the piping, the longer the runs, the more heat, the more energy loss. Um, so it's even more critical in these applications to control the circulation pump. Next slide, please. So in a commercial demand control, they work differently than the residential. It uses an inline flow switch that detects draw flows in the building, and then it also checks the return line temperature. So the sequence of operation here, um, if you go to the next slide, if you look at the sequence of operation, anytime someone's using hot water in the building, that flow switch is sending a signal to the controller, and then it's checking return line temperature. If the return line is hot, the pump stays off. If it's fallen below its target temp, the pump turns on and it just runs for however many minutes it takes for the return line to reach its lockout, and then it shuts off. For the system that we provide, that Innovative provides, we have a thing called Auto Prime, which is optional. And what that does is that it simulates a draw flow after a set period of time, and that is to ensure that in large distribution systems that there isn't a case where enough time goes by where the system gets completely ambient. Because for these types of buildings, we never want the system to get to an unusable hot water temperature, because then when the pump turns on, then the users are still going to have to wait many minutes for the hot water to get there. So that's the difference between the commercial and residential. So yeah, that next slide there, this is a picture of the flow switch that we have in line in a plumbing system in an apartment building. But those are the primary differences. Um, let's see, I can't hear anybody. I was going to maybe use this moment to answer any questions. Um, let's see. Is there any questions? Jason, can you hear me? Okay, okay. Jason just texted me. He said I'll ask him at the end. Okay, no problem. Moving on, let's talk about building energy codes. So every state in the country has their own building energy code that they uh, adopt or conform to. Um, in California, we have something called Title 24, which regulates our building energy use. And so there's two different pathways that you can take. You can take a prescriptive approach, or you can take a performance approach. The easiest way is the prescriptive approach, because that basically you just, you know, do things in a very sort of cookie cutter way, check the boxes off, and you get your energy plan stamped and approved. Um, let's see, Jason's asking me. Okay, I hear you, Jason. Whoops.
You can't hear me,
Okay.
correct?
Um, we have Title 24 prescriptive. It's now it's been a prescriptive requirement since 2013. So for single family homes, if a builder is putting in a recirculating pump, it has to be on demand to meet the prescriptive approach. So timers don't qualify; they're prohibited. Well, they're not prohibited. So this is to make the distinction. It's not a mandatory requirement in the sense that if you have a recirculating pump, you could put a timer on it, but the penalty that you get from an energy standpoint, there's literally no amount of additional insulation that you can put in the house that'll make up for those lost energy points. So even though it's technically not a mandatory requirement, there's really no way around not putting in a on-demand control versus the alternative. So this is the same for both single-family and multifamily dwelling units. EPA they've published their own guidelines for efficient hot water distribution. So for the water sense certification, you have to have no more than a half gallon of water maybe stored in any piping or manifold between the hot water source or any hot water fixture. So in other words, that if you have a recirculation loop, right, and you off the loop you have branched out into the to the fixture, you can't have any more than a half gallon of water. Now the goal is to get that down to 1 or 2 cups of water. So there's only 1 cup of water in about 5 feet of half-inch copper pipe. So if you can keep those branch lines to about 10 feet, 10 to 12 feet of half-inch copper or half-inch PEX, then you're never going to wait more than a couple cups of water for hot water. Recirculation systems must be demand initiated. So water sense and also lead so lead has the same requirements here, that you have to minimize the amount of water that's in the plumbing. So so the goal is to keep the pipe sizes low. The pipe sizes, the pipe size diameters low, and keep them short. Now, if you're not going to do a recirculation loop, then the next best option is a compact plumbing design. A lot of builders will tell you that's not as practical because it's hard to keep the water heater centrally located in the house. But if you're able to achieve a compact plumbing design, then that's pretty much as efficient as you can get it. Okay, next slide, please. So finally, the IECC is what regulates most states' building energy codes. Texas has formally adopted the latest 2018, although I know that it's a city by city type of adoption. But starting in the 2015 code is when they started to require demand recirculation for buildings that have recirculation. So if you look at the second paragraph here, that controls for circulating hot water pumps shall start the pump based on the identification of a demand for hot water within the occupancy. The controls shall automatically turn off the pump when the water in the loop is at the desired temperature. What's interesting about the IECC is that they change, just like Title 24, it changes every 3 years. And if you look, starting in 2009 is when they started to require recirculating pump controls, and then every iteration they've been getting more definitive about what that means. So if you look at the language of the code from 2009, 2012, 2015, and now 2018, this is the most defined that they've had as far as having it be on demand. So if you look at the next slide here, this is the very next section of the energy code, where it tells you what a demand recirculating system is that it receives a signal from the action of a user of a fixture or appliance, or sensing the presence of a fixture. So a signal from the action of a user would indicate like a push button activator. Sensing the presence of a user or of a fixture is motion detection, or sensing the flow of hot water, and that's the flow switch. The controls shall limit the temperature of the water entering the cold water piping to not greater than 104 degrees. So this is talking about in a trunk and branch line situation where we're using the cold water line as the return, where we're not going to let any more than 104 degrees into that cold water piping. Now, Title 24 actually has even more definition about that. They require that on-demand pumps have an automatic 5-minute timed lockout. So from the time that the pump turns on, after 5 minutes, no matter what, it's supposed to turn off. So even if that return line doesn't hit temperature, it's supposed to turn off. And that's to prevent the pump just from, if there's airlock and the pump's not reading temperature, it's going to prevent it from cavitating and from burning out. Anyway, here's just some example cities that are currently on the 2015-2018 IECC. I just pulled these from the list, but the vast majority of cities right now in Texas are on the 2015 or later. All the biggest cities are listed here, but if you want to see the full list, there's a link right here that'll take you to the State Energy Conservation Office to show you which states are adopting which version of IECC. Okay, next slide.
Oh, hold on. I'm coming. There we go.
So let's say you're an inspector, a city inspector or a plumbing inspector, and you want to verify that there's a demand control in place. So, you go into the water heater room, you can see the recirculation pump, but how do I know if it's on demand? It's actually very simple. All you have to do is just ask for the where the activation sensors are. It's either going to be hardwired or wireless. So you actually need to get inside the dwelling unit and verify that there's sensors that are connected to the pump that to turn it on. And also, if you're looking at the return line, and the return line is hot, then that pump should not be running, which would mean that there is a temperature sensor or an aquastat on that return line. So those are the things that you should look for. And there's a number of manufacturers that make an on-demand system. So, if you just kind of, and it's not a very extensive list. So if you know who the people are that make on-demand systems, then that would help clarify that as well. But you also want to be clear about what is not a demand control. So timers and time clocks, which is by far the most prevalent type of pump control that's out there. That is not an on-demand control. That is a timer. An aquastat by itself is not a timer. So those two, either by themselves or in combination, do not meet the code. Also, these so-called smart or learning pumps, they're not in the classification of on-demand. Maybe at some point the codes change to allow smart or learning pumps, but I think before we get there, we have to understand the control logic that's behind it, because right now that seems to be a little bit fuzzy, and there's no real standard on that what that logic is. And then variable speed drives are again, you'll know if it's a variable speed drive because the pump will be running continuously, just at a different speed. So that's all I have. I appreciate you guys taking the time and learning about on-demand. Maybe some of it was new to you, maybe some of it was review, but hopefully you learned something new. Let's see. So I can't hear anything, but Jason is texting me, and he's saying the questions will be answered in the email from Spear that will also have a PDF of the slides. And also there will be an evaluation that will need to be completed for your ICC CEUs. So there you go.
Can you hear me at all? Still can't hear me.
I wish I could communicate better with you guys, but
now
again,
can you hear me?
For paying attention, and you've got my contact information. Feel free to call or email me directly with any questions, and have a great day, everyone.